Our next speaker is Daróczy, who will speak about generalization of band via estimate of tangent sensitive tensors of ReLU networks and of the H2 H2 norm of neural OOTs and SSMs.
All right, thank you.
Long title.
I hope at the end you will be familiar, at least that's what kind of things these kind of things are. All right, so before I start, I was thinking about that since GPU Day is more than 10 years old, and I was here several times, and I was thinking that what kind of problems did we have in the old day and nowadays, and I realized that a lot of problems I no longer have to deal with them, but there are new ones, and there are some interesting things. So from the perspective of machine learning, I think there are several things which we can say. Of course, you can argue with it, obviously. So I think in the early 2010, everybody wanted to have some kind of real-time inference times to object detection or just classification or something like that. That was the goal. And in the mid-2010, I think we achieved, at some extent, we achieved that. And of course, at the time, the GPUs were really fast for these kind of things. So inference was, in a way, was more almost real time if you have the state-of-the-art GPU at the time. In the late 2010, the new challenge came from the idea that maybe these models are not good enough. We have to constantly learn. We need to use the feedback. And of course, reinforcement learning emerged again because of a lot of talks where we were thinking that reinforcement learning RL will be the solution. And this is still, of course, an ongoing topic. But then came the idea that maybe learning and inference should be parallel tasks. So we have to learn, and meanwhile, we have to infer. And I think right now, the main question is that how to identify what to learn, when to learn, and when to continue learning. Because we have a lot of models. We have a lot of existing models for transfer learning or coming from totally different data. But usually, we don't know what's going on, how to measure the quality of these methods on unknown parts of the distribution. So it would be nice to understand, nice to measure somehow the true error, not just the estimated error, which is the loss on some kind of test set or the training set. But how to do that? We need to, that's the goal of my talk, to establish some kind of generalization bounds and try to identify these generalization bounds via some kind of measures which are actually on the fly computable. And to do that, we will be focusing on 3 different type ones. Why I'm showing 3 is because I wanted to show you that even if the ReLU networks, the rectified linear unit, simple feed-forward, multi-layer perceptron convolutional networks seems to be known at some extent, and we will show results on that mainly. But there are some new and more challenging ones. But to understand actually what we are trying to deal with, I think it's good to try to understand what kind of topological spaces are related to these kind of problems. So the first one is the observations, the data. What we assume, usually nothing, which is not true because we usually assume some kind of boundedness. So we assume that if it's not bounded, we will norm them and so on. So some kind of knowledge is known. But outside of setting them into a compact set, nothing else usually, because we say that all our models are distribution free. Of course, it's not, if we know something about them, usually all the generalization bounds will be much better. These are the peg-based bounds. The second one is the error surface. This is the loss surface. This is actually the loss surface, a very simple model. And what we are doing is that we are trying to go down to some kind of local minima with gradient steps, and you can see that the gradient steps are the green ones. The last one is more trickier. These are the hyperparameters. These are usually discrete. The size of the network, the number of trees in a boosted tree, or any other things like how many parameters do we have, what are the parameters of the algorithm, what we use to learn, and so on. But for different problems, we have different kind of observations, error surface, and hyperparameters. Like from learning for pairwise comparisons, it seems a simple problem. It turned out that it's a very complex problem because there are a lot of things which is hard to prove. But the observations are just binary outcomes. We have a graph, an underlying graph. The error surface could be simple L2 loss or something like that. Feed-forward networks have data label pairs, and deep structured space-based models or neural ordinary differential equations usually use sequences. So what to do with them? And of course, to understand where we are and how can we trust the solution, that we have to somehow identify the geometry of these topological spaces. And that's the trick, because the loss is just a local measurement. At the time, we have that loss on our estimated loss. That's not enough. So before we go into that, I want to show you some recent results on where we are going right now. So there was a mention in one of the talks about the structured space-based models, which are actually state-of-the-art for long-range benchmarks. So not for shorter ones, long-range benchmarks. And they are even beating out the transformers. So I think we should be focusing on them, at least checking them out. Neural ODEs are a bit different. They are very elegant models where the depth of the model is actually continuous technically. Of course, in practice, we will do some discretization, but they can be really good. They can perform really good, and there are some recent results where they are performing very close to the state-of-the-art results on ImageNet. I just show you 2 examples that are very simple. Neural ODE learns a sinus and solves the pendulum problem with a very simple structure. It's fast, it's elegant, and it's a neural networking. So these are recent new type of neural structures, in my opinion. So let's say we try to identify what is the problem with learning in case of generalization. So generalization has the following problem. When we are learning, the main goal would be that we try to make the expected true loss as small as possible. So try to find a hypothesis which will make it the minimal. But the problem is that we don't know actually the true distribution, so we cannot we can only approximate it with some kind of empirical risk, which is actually just means that we have t samples and we are measuring the average of it or some kind of mean. It could be, of course, mean, not just the average. But the question is that can we trust what we found based on the empirical risk? And the solution, there are two actually we have some kind of parameters. So if we have some kind of metric connected to the parameter space, we can measure the difference, the distance between the true optimal one and the one we found, right? But the surfaces, just look at it. The surface could be really, really tough. This is just a logistic regression. The surface of a neural network looks way worse. So we cannot trust that if you are close, you will perform similarly, okay? That's the problem. So we don't have to measure actually. Then there is another problem. It's not bijective. usually we are over-parameterizing. There are multiple parameters achieving the same loss, the same true loss. We don't, it doesn't matter what is the parameters, unless we will care, because of one thing we will care about that. But there are multiple solutions with the same loss. The other one is that we are trying to identify the generalization gap, where we are estimating the loss on a fixed finite set. And our goal is to upper bound these difference, the true loss and the estimated one. At first, it seems that how, right? We don't know the true loss. How can we do that? Here comes the old statistics and probability theory. I think you have some guess what we use in all this, the Chernoff, the Hövsing, and all these kind of bounds. So the concentration of bounds. But there is an elegant framework, which is obviously based on those kind of old ones, which is called probably approximately correct learning, which seems a bit strange name, but we call them POC bounds. The main idea is that we are establishing a high probability bound that these will, so in this case, it means that, of course, if the probability that this amount will be upper bounded by one of the hypotheses, the difference will be high, is low, given that R is low. So what's going on here is that we try to establish these kind of bounds. So what we have to identify is what is this R. And I call them R in this case, but of course there are some different versions. The POC-based bounds is one of the ingenious ways to extract this idea, because the main idea is that, of course, we have an algorithm, we have a data. We cannot achieve, if we have a large hypothesis class, we cannot arrive at any of them. So there are some subset which is possible, and with that knowledge, we can have a tighter bound. But of course, it depends on the data. So it's a bit different. So these are general ones. So right now, I will show you some kind of POC bounds which are actually general and not depend on the data. So the main idea is that we are trying to identify this R, and this R is actually is based on the Rademacher complexity of the hypothesis class F on the set X, because it's the empirical Rademacher complexity. Okay, some results, some kind of things, how they are, they look like usually. So usually a good PEG bound have two properties. The first one is that it should go to 0 if the number of samples is going to infinity, right? Because we want to have some kind of convergence. So if you see the square root of t here, then we are usually say that it's a good one at some extent. The first part here is about the parameterization of in this case, the Neuro-Odious. It's a recent result, which is actually using the Neuro-Odious infinite norm. The second one is also using a similar neural audio structure, but under stability, where this C is actually lower than that. So where we use the H2 norm, the weighted H2 norm of the dynamical system behind the neural audio. I will not define that because we don't have time for that, but the main idea is that actually we can identify somehow that the system's output is just an inner product in a Hilbert space, where actually the system, the parameterization of the neural audio acts just as a transformation. And in this case, we can have an upper bound on the Rademacher complexity. That's the trick in the proof. And the similar thing can be done for deep structural space models, where the solution is a bit more complex because it's a stacked one and a lot of things are there. But the main trick is that what I wanted to just show you, that every single bound, what you can see in this page, is connected to the norm of the dynamical system, which is usually not depending on the number of parameters, which is a very important thing, because that was the main problem before, that usually people were obsessed with the idea that that if you have a large network, maybe it will overfit, but it will not overfit if these norms are small, because in this case, the dynamical complexity will be low and your generalization bound will be good. So, but to achieve this, there is one thing we need: stability. Even in the first case, there were some kind of stability involved, but actually it was time independent, and with the time independence, it forced in a way, and some bounded norms, it forced into stability, but it was not stated. But the key information here is that we need to upper bound the norms or control the norms, and with stability we can do that. Okay, for feed-forward networks, which are the old ones, so we have discrete number of layers and so on. So there was some results where these are the weight matrices in the layers, and these are the infinite norms. So this is actually a pretty conservative norm, unless we are assuming additional things. It can be also connected to a new, a different kind of norm, which is called tangent sensitivity, and it's actually smaller than the first one. And what I want to show you today is that actually it's a bit tricky, because calculating these norms is easier. These are tighter, but the computation of those ones are much harder. So it's a trade-off. But again, both of these bounds, and this is actually the standard bound what we say today, unless we assume a lot of other things. Okay. Question is that are these meaningful? Because I'm saying although and all these kind of things. So technically, are they useful? Yes. So the first meaningful bound was published in 2017, when they proposed that under some kind of data dependent prior under 0.1665 will be the generalization bound, which means that if you are measuring on the training set like 90, you will be not doing less than 74, which is great. Because on NNIST, okay, of course, every single model is performing 90 plus, but to have some kind of meaningful bound, we should have it under 1 if the error upper bound is 1, right? Now, recently, oh, I forgot to mention who wrote that, but it's 2%. So it's very small. So these are starting to be meaningful. But for bulk bounds, the first meaningful is this year. So it's a new thing. And it's 0.6062, 162, but it's not uniform. So that's why I want to show you one thing, that if you look here, this is the generalization gap, and this is some version of the tangent sensitivity. And technically, you can see that they are correlating, right? It's pretty close. Per category 2. It's on CFAR, as I remember. Maybe that's not CFAR. I don't remember which ones. Sorry. But the main point is that these are more uniform, but the bounds are actually the supremum of the bound is a bit higher. Technically, my student is working on to have better constants right now. So hopefully we will have them. So the question is how to calculate them. One more thing. This is for neural audios. Here the bound is after a while is also non-vacuous. So here it's lower than the true loss was. True gap was when we have small number of samples. So the question is how to do anything, how to calculate these. So why we need that? The question is how to calculate this. No? So naive implementation is usually not working. So we can how to calculate the tangent sensitivity. It's a lot of calculations. It's a parameter times input dimension times output neuron size tensor. It's very large. Just imagine that input could be 1 million pixels. So it doesn't work. We need to backpropagate to get the gradients, then differentiate again. A lot of things. Memory, computational time is crazy. But we know that it's much more structured for ReLU networks. So I'm going to show you some results why ReLU networks work and why these are actually meaningful. It looks the following. So what is a ReLU network doing? It's actually cutting the input space into some kind of regions. So the first layer cuts like that. It's a typical hyperplane arrangement. But the thing comes next. Then every single region have different kind of cutting on the second level and the third level and so on. So every layer is cutting it into smaller regions. And the idea was, if you actually try to make some kind of polarization of it, it's very nice. So the question was, what can it approximate? So the idea is that because if you have a deep enough network, maybe you can describe a lot of really complex surfaces based on that. But how to do that? What is the actual technical bound for that? They try to understand what's going on, and I think it's a very interesting way to describe it. So Montufar and the others propose this wonderful picture to identify to show that what's going on. So it's like you can do it on a paper. So you are just cutting the plane and folding and cutting and folding, and then you can see that you can differentiate the points. But the question is how stable this configuration, that the number of regions are actually more like linear in the neuron size than not linear. Before that, usually they said the number of regions are exponential with the depth and the neurons and so on. It's not. In practice, it's not. Even just in one case, it started to be much larger when it needs to be memorizing something. How they forced it? They gave the network corrupted labels. So in this case, it cannot generalize anything. It will force to try to separate every single element. So how can we use this knowledge? So we know the number of regions are small, not small, but not exponential. We know that it should be through sparsification. What is sparsification? Here you can see that if we are calculating the important weights in the gradient, the actual labels will be different per category, and at the end there will be pets. So how to calculate pets? There will be some kind of based on the pets, we can easily calculate the tangent sensitivity. We just memorize the pets which are there and just calculate the pets with making a product of the weights. And based on that, we could achieve more than 20 times gain in calculating the norm. And then it's actually good to do it. So this is my last slide. So just one thing, I think quality monitoring of constantly learning models is possible right now. Over parameterization, the double descent effect and all these kind of things are not a problem because we need to constrain the norms, not the number of parameters, stability, and explicit, or we need to have that either from the algorithm or explicitly putting it into the loss. So I think if we are trying to understand what's going on in the background, we can do that right now. I hope in the near future we can do that for SSMs and ReLU audios too. Thank you very much.
So we have a time for a few questions.
With the technical question that you have shown a formula when the upper bound of the R is the norm of the weights, the product of the norm of the weights. Yeah, that is exactly. It's does it mean that it's a good idea to normalize all the weights or the layers to one?
That's what we are doing.
Okay.
So regularization is usually with weight decay, which is just the add to norm of the weights, and it's technically doing that. But of course, there is a better one when you are doing that regularization, which means that you are trying to regularize the paths between input and output. Or the other one is that you are trying to optimize per layer. In this case, it's getting better.
I'm not an expert in the theory here, but I wonder if there are any like numerical experiments to confirm these theoretical results, if there are any hidden assumptions that may invalidate them in the practical implementation, right? So I have an MNIST classifier implemented somehow, and I may have violated something, but I assume the theoretical bounds, right? Is there any check I could do to verify that, yes, this very high upper bound that these results are claiming is indeed true up to some degree, like some Monte Carlo simulation or something.
Yeah, that's what's going on here. So so these are actually like that. So what they did, that for a particular element, particular network, they actually calculated all the constants in the order. So they have the exact Rademacher complexity. So they know every element, and then they got this number, and then they confirmed it with they didn't do any plots, but because it's a guy alone, but actually it's true, you know. So numerically there is numbers that yeah.
Okay.
So that's why we are trying to have non-recursive bounds when we know exactly what is the bound, not just some kind up to constant.
Okay, thank you.
The reason why I showed the constant the orders, because otherwise it would be really a large formula without any takeaway message. So
We have time for a last question.
Thank you. At the beginning of your talk, you mentioned continual learning. So you
Yeah.
proved formulas how well your model generalizes, but what does it tell for us in the case if we want to do transfer learning or do a model that performs in different domains? Do you give us some bounds for that scenario?
yeah, they are constant. So there are some continual learning bug bounds, but I actually are working on one, which is actually working not like that in the literature. So it's an open question, but I think the things are very similar. So yeah, but yeah, that's a problem. For PUG-based, it's a problem actually, because then the data dependency is done. But for PUG bounds, for Rademacher, it's doable.
So thank you for your talk, and time for our next speaker, which will be good.